from Lab 1.3 on recrystallization, and we'll talk a little bit more about that later. All right, back in chapters 1 to whatever, we talked about hybridization. We said that carbon has a valence of 4. It will typically form 4 bonds. We can have single bonds around our carbon, sp3 hybridization. We can make a carbon-carbon double and triple bond. In a double and triple bond, we said we take p orbitals and they form a pi bond. So we have 1 sigma bond for this compound, 1 single bond, and 1 pi bond. For our triple bond, we have 1 single bond, 1 sigma bond, and we have 2 pi bonds. Well, these 3 types of carbon compounds make up the functional groups of alkenes, alkanes, and alkynes. In an alkane, you will have a compound where the general formula is Cn, n is some integer, and we will have 2n plus 2 hydrogens. All carbons will be sp cubed. Everything will be tetrahedral. In an alkene, our general formula is going to be CnH2n, so we're missing 2 hydrogens for every double bond, that is. It will contain at least 1 sp squared set of carbons in a carbon-carbon double bond. Alkynes, CnHn, and again, we can have other things attached, but it will contain 1 sp hybridized group. Examples of other functional groups. Like we just said, this is an alkene. It'll have a double bond, and again, we can have anything else attached to it. It must have at least 1 double bond. If we have an OH group, this is the oxygen. Again, doesn't matter what's attached to it. This is an alcohol. If we put the oxygen here in between carbons, we get an ether. Now, the whole notion of a functional group and functional group chemistry is to make organic chemistry very easy for you. Okay? Very easy. That's because virtually all alkenes will undergo very, very similar sets of reactions. So if you see a compound, regardless what else is attached, and it has a double bond, you know a single set of reactions that will undergo. For example, if we have an alkene, now this is just a generic sort of thing, just a double bond. We can react this with bromine, usually in a solvent like carbon tetrachloride. We will form a 1,2 dibromide. And not only that, but the stereochemistry, the orientation of the 2 bromines are going to be anti or trans to each other. These will always involve what's called a bromonium ion intermediate, and that's what gives rise to the trans stereochemistry. We'll talk a lot about this when we get to the chapter on alkenes. But the important point is, it doesn't matter what else is attached to your alkene here. If it has the double bond, this is one of the characteristic reactions it will undergo. So that actually makes it all really simple for you. There are a number of functional groups, however, that we must remember. We're going to deal with the chemistry of these as we go through the course. Alkanes, like we said, they only have sp cubed carbons. An example is this, where we have 2 together. This is ethane. Alkene, carbon-carbon double bond. This would be ethene. An alkyne, triple bond. This is acetylene, or more properly, ethyne. If we take our double bonds and we place them in a ring, we saw benzene last time. 3 double bonds in a ring like this. This is referred to as an arene. Benzene, remember, is a very special type of alkene because it is very unreactive in the typical alkene reactions. We can add heteroatoms. If we add a halogen, and when we use an X here, that refers to any generic halogen. This is just simply referred to as a halide, alkyl halide. Usually, this is bromomethane. As we saw, we have an OH group. It's an alcohol. We'll call this methanol. This is wood alcohol, not the stuff that you would consume. For that, you need one more carbon out here. That would be ethanol. Put the oxygen in the middle, we get an ether. This is dimethyl ether. We can attach an amine. This is methylamine. Remember, the key thing to think about in amines is we have this lone pair of electrons up here. That's going to define all of the chemistry of amines. Carbon, nitrogen, triple bond, equivalent to cyanide, if you will. This is a nitrile. This is called aceternitrile. Nitro group. This is nitromethane. Thiols. Now, thiols are the sulfur equivalent of alcohols. Instead of an OH, we have an SH. The unique things about thiols is that they really, really stink. Really stink. Butane thiol is the essence of skunk. Same thing with sulfides that are really bad too. If this was an oxygen, it'd be an ether. Here we have dimethyl sulfide. Now, a very important group that we're going to talk about, well, we'll talk about it now, but that we'll study their chemistry next semester, are things called carbonyls. Carbonyl is defined as a carbon-oxygen double bond. The carbon and the oxygen are both sp squared in this functional group. We're going to name these depending upon what's attached on the various sides of the carbonyl. If we simply have a hydrogen, that's referred to as an aldehyde. This is acetaldehyde. If we have carbons on both sides, that's a ketone. This is acetone. Acetone is a very common solvent. We will use this in the lab. It's also fingernail polish remover. If we have an OH attached to one side, this makes it a carboxylic acid. We saw this when we talked about acids and bases. This is a weak acid. This is acetic acid. Again, it's the acidic component of vinegar. If instead of an OH we have an O attached to a carbon, that makes an ester. This is called methyl acetate, methyl ester of acetic acid. Amides. If on one side we have a nitrogen compound, that's an amide. This is acetamide. The amide is the backbone of proteins. But a halogen is an acid halide. This is ethanoyl chloride. And finally, if we have symmetry here, so we have carbonyl, and then this is the equivalent of a carboxylic acid. It's referred to as an acid anhydride. If we add water to this, we would get 2 moles of acid out. Now, there is no really easy way to deal with functional groups, okay? We're going to talk about them one by one as we go. But you really do need an overview of all of these. And it's worth taking a little bit of time to review them and making sure you know what's what. At the end of class, we will do an exercise where we'll look at compounds and identify functional groups. Any questions? All right. We saw this guy before. This is a little hyperactive molecule with 5 carbons. And the point of this little video was to demonstrate exactly how dynamic carbon compounds are. Remember, anytime you have a single bond, you have free rotation about that bond. Not only that, but the molecules vibrate, they obviously wiggle, they breathe, they do all sorts of things very, very, very rapidly. We're talking 10 to the 6 times per second. To look at this in a static way, if we had drawn a compound like this, so this has 1, 2, 3, 4, 5 carbons, and a 2-carbon chain sticking up. If we had drawn it like this, that's a pretty fine, acceptable way to do it. But we can also draw it like this. The point is that because these bonds rotate so quickly, these are not distinguishable. And we're going to refer to these as conformational isomers. An isomer will have the same numbers and types of atoms, but they'll be arranged differently somehow. These are arranged differently simply based on their conformation. Again, because they rotate, they interchange so rapidly, we just consider these the same compound. Now, this means that if you're drawing an answer to a structure or something on an exam, you can draw it any way you want. That just means I have to take extra time to try to figure out what the heck you're doing. But, okay, that's legal. Do try, however, to stick to the more conventional presentations. It just makes it easier on everyone. Let's just look at a couple examples here. These are all conformational isomers. If you look at this guy up here, we can identify a 1, 2, 3, 4, 5 carbon chain. And here on the middle carbon, we have a 1 carbon chain sticking up. Same thing here, just a different arrangement with our 5 carbon backbone. Here we're going down, but it's up. These are all exactly the same compound. And you could draw them in any of these conformations. Now, something like this, however, is typically preferred. The other type of isomerism that we're going to talk about today, aside from conformational, is constitutional isomerism. Constitutional isomers. Because they're isomers, they will have the same numbers and types of atoms, okay? But the difference between conformational and constitutional is that these guys are arranged differently. Their constitution, their connectivity is different. Here's an example. Here's a little 5 carbon chain with a 2 carbon side chain that we talked about. This is C7H16. Make sure that you can do this too. Remember, that's a CH3. All 3 of these are CH3s, CH2s, and a CH. C7H16. This is also C7H16. They are obviously, however, different compounds. Simplest way to see that is to look for the longest chain. Here we have a 5 carbon chain here. Here we have a 1, 2, 3, 4, 5, 6 carbon chain, 1 carbon side chain, 2 carbon side chain. When you look at conformational isomers, you need to be able to look at the compounds. First of all, come up with a formula to decide if they're isomeric at all. And then secondly, be able to distinguish, probably the best way is to look for the parent chain, whether or not they are indeed the same compound, or if they are constitutional isomers. Now there's a little game that's fun to play with regard to constitutional isomerism is called this. Would you please quickly write all of the constitutional isomers you can manage to do having the formula C3H8? Well, this is a game, but this really isn't so difficult, is it? Because there's really only one way you can do this. We're going to attach all 3 carbons in a row. It's in here is 3, so 2n plus 2 is 8, so it's an alkane. Only one way you can do it, and that's to write this molecule here. Only one way. So there are no other constitutional isomers. Everyone see this? Well, let's make it a little more interesting. And let's do C3H6. We're going to string our 3 carbons together again, but we only have 6 hydrogens. Remember, this is Cn, and this is H2n. So we're dealing with an alkene, aren't we? That is a carbon-carbon double bond. Only one way you can make an alkene, and that's like this. 3 carbons, 6 hydrogens. There is, however, one more constitutional isomer here. What if we took our 3 carbons and we put them into a ring? Make a triangle. We'll refer to this as cyclopropane, and again it's 3 carbons in a ring and 6 hydrogens. These are our 2 constitutional isomers for C3H6. Okay, everyone know how to play now? Let's do C4H8. We're looking for 5 of them. Well, here's what I got. We were at CnH2n, so we're dealing with a double bond, right? So we take our 4 carbons, stick a double bond in the middle, stick a double bond on the end. Now remember, if we put it on this end, it'd be the same compound, wouldn't it? Just flip it around. We can put it in the middle this way with these 2 guys sticking out. We can make a ring, just like we did. There's our 3-membered ring with 1 side chain, or we can take our 4 carbons and make a square. Each of these is a CH2, so that's 8 total hydrogens. We can stick in like an oxygen. There are a couple here. C2. So only 2 carbons. They have to be, well, they're going to have to be connected to each other because we have the oxygen. Remember we said the oxygen can form an alcohol, an OH, or it can be in between as an ether. First way to do it is just to take the 2 carbons, stick them together, and then put an OH. And the second way is to put the oxygen in the middle with a CH3 on both sides. Once again, this is an alcohol, and this is an ether. Now, just to show you how quickly this can become complicated, this is the one that was on the exam. C3H6O2. Gee, only 3 carbons. We can do this, right? So you get a point for every one you draw correctly. Well, let me just show it to you. So, and you can practice this on your own. It's kind of a fun problem. C3H6O2. Here we've made an ester. Here we've made another ester. This is yet another ester. This is an aldehyde and an alcohol. This is an ether. So is this. But we're not done yet. You can also do all these guys. These are all legal isomers, constitutional isomers of C3H6O2. Organic compounds can get very, very complicated very, very quickly. Any questions?
I have a question.
Okay.
So each of these molecules, they're different. They're not the same.
They're absolutely different chemical
If they're
compounds.
conformational, they would be, even though they're arranged different, they would be the
They
same.
will be the same, right. All right, the other game that we play with isomers is this one. Here I give you 2 compounds, usually in different representations, and ask you, are these identical? Are they constitutional isomers or different chemical compounds and not isomeric? Yeah.
How do you know how many different isomers you create?
Just sit and talk. There is an algorithm that will tell you, but it's very complicated. It really is. Once you get above the very simple ones, I have a little computer program that will generate them for me. So that's cheating, I suppose. But, yeah, it's complicated. All right, so look at these. Are these identical? That is the same compound. Are they constitutional isomers? Are they different and not isomeric? What I would do here is I would look and say, well, what is this? This is 1, 2, 3, 4, 5 carbons and 12 hydrogens. What's this guy? 1, 2, 3, 4, 5, 6 carbons in a chain and 14 hydrogens. These are different chemical compounds, aren't they? They have different molecular formulas. All right. How about these 2? Well, this is a condensed formula, isn't it? Remember, we're going to define our chain this way. We have 1, 2, 3, 4, 5, 6 carbons in our chain. And we have 1, 2 fluorines. The first fluorine is here. If we started at this end, it would be on the second carbon. The next chlorine is on the carbon 1, 2, 3, 4. The formula here, well, I didn't do a formula. 6 carbon main chain, chlorines in positions 2 and 4. Over here, we have a 1, 2, 3, 4, 5, 6 carbon main chain, right? We have a chlorine in position 2 and in position 4. These two guys are the same compound, aren't they? They are simply different representations, but they're the same compound. Yeah. Oh, okay. Six carbon chain, 1, 2, 3, 4, 5, 6. Chlorine and carbon 2, chlorine and carbon 4. Same thing.
I have a question.
Yeah.
The chlorine in the middle, you say that it's on the second carbon.
Right.
Why not first?
Well, because there are already 3 hydrogens on the first. So when you draw a condensed formula, if there's a substituent here, it's after the carbon that's in the main chain. So this means this carbon has a hydrogen and a chlorine. It is bonded to this carbon that has 3 hydrogens. Yeah?
So are they constitutional then?
They would be conformational isomers, if anything. How about these two guys? We have a chain here of 1, 2, 3, 4 carbons, double bond, and we have a CH3 side chain. Total of C5H10. Over here, we have 1, 2, 3, 4, 5 carbons in our chain, and 2 CH3 side chains. C7H14, these are different, aren't they? They are not isomers, they are different chemical compounds. How about these alkynes? This is a carbon, isn't it? We have 1, 2, 3 carbons in our chain. Triple bond and 1 chlorine. Over here we have 1, 2, 3 carbons in our chain. Triple bond and a chlorine. Chlorines are both in position number 1. These are identical compounds, aren't they? One more simple one here. These are amides, aren't they? Have a carbonyl, and we have a nitrogen attached to one side of our carbonyl. Here we have a 1, 2, 3 carbon chain, and then an NHCH3. We also have a CH3 hanging down through here. This comes to C5H11NO. Over here we have 1, 2, 3, 4 carbons in our chain. We have an N methyl group, and of course our carbonyl. It's also C5H11NO, but because we have a 3-carbon parent here and a 4-carbon parent here, these are constitutional isomers. Now, I'm going to be entirely honest here. All of those are very simple, aren't they? This is the one that was on the exam.
Yeah, can we fix that? I said, can we fix that? Just stick with these. You write the exam, right?
Yeah.
Yeah. So can we switch them out?
Oh, yeah.
Yeah.
Everybody got it right. First thing we have to do, this really is a real compound. Organic compounds are amazing. You can just tie them in knots. First thing we want to do is figure out a formula. Okay? Look at this guy and count how many carbons we're dealing with. Have to start somewhere. If we started here, we would have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 carbons. How many hydrogens? These guys are CH2s. So are these guys. So is that. And these are all CHs. They have 3 bonds. If we sprouted our hydrogens, they would look like that. And if you very quickly counted them, you would have C12H14. All right. How about this guy? What's its formula? One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 carbons. CH2, CH, CH3, CH, CH, CH3, CH, CH, and a hydrogen here. My gosh, it's C12H14. So what are these two? They're clearly not the same compound, are they? They have the same molecular formula. They are constitutional isomers. Looking at a compound like this and even getting the formula is really good practice because it allows you to practice reading these things. All right. I'm really tired of talking about 1-carbon side chains and stuff like that, CH3s. So we're going to start nomenclature. Let's think about how we would name some of these compounds. So we're going to start off with the very simplest functional group, and that is the alkane. First thing you want to do in an alkane is identify the parent. The parent's going to be the longest continuous chain. That's going to give us the root of our name. If we have 1 carbon, our root here is meth. We would call this methane. 2 carbons would be ethane. 3 carbons, propane. but, pent, hex, hept, oct, non, dec, and then here's others that I can't remember either. You really should be able to count to 10 though. Meth, eth, prop, but, pent, hex, hept, oct, non, and dec. If it is a simple straight chain alkane, all you do is add the suffix A and E to the prefix depending on the number of carbons that you have. So that's very simple. We also have things called alkyl groups. In many of the compounds we looked at, we had side chains, right? If we have a side chain with one carbon, we say this is a derivative of methane, and we will call this a methyl group. So we say we have a one carbon side chain, that is, we have a methyl group at some position along the chain. If we had a two carbon, we would call that an ethyl group. Another example here, a couple more where we use this. This is an alcohol. We would call this methyl alcohol. This is an amine. We would call this methyl amine. So when you see the YL, that tells you you're dealing with a substituent that's attached to something else. The full set of them looks something like this. Methyl ethyl propyl pentyl. There are also a lot of trivial names that have come up over time. Isopropyl, isobutyl, etc., etc. We'll deal with those in just a minute. They're branch chains usually. But this is our simple chains attached to a parent. Okay. The other thing we want to be able to talk about when we're looking at simple carbons, simple alkane carbons, is their connectivity. There's actually a fairly important way to describe the connectivity, and that's using primary, secondary, tertiary, whatever. What it simply refers to, we look at a carbon that we want to identify, and then we say how many other carbons is it attached to. If it's attached to one, that's a primary carbon. If it's attached to two other carbons, secondary, three carbons, tertiary, four carbons over here, this would be a quaternary. Fairly simple. Let's just look at an example. Very quickly, take this guy and pick out the primary carbons. Primary carbons, remember, are attached only to one other carbon. Therefore, this is our parent chain here. This is a methyl group. It's primary, and both ends of this are also primary carbons. Secondary carbons. Well, we know a secondary carbon is attached to two other carbons. The only one that meets the criteria here is this guy right there on our chain, attached to two other carbons. And finally, this guy here is a tertiary carbon. It's attached to one, two, three other carbons. Fairly simple. This is a type of nomenclature that we will use a lot when we're talking about things like carbocations, radicals, whatever. Any questions? All right, let's go ahead and do some standard nomenclature. Step one, If we have a branched alkane, that means we have a parent chain with things hanging off. We want to first of all identify the longest continuous chain of carbons. Our first one here, that's really simple. 1, 2, 3, 4, 5, 6. Here, our longest chain, we'd actually start up here, wouldn't we? 1, 2, 3, 4, 5, 6. Longest chain here, not this one. We would go this way. Our first one here, 6 carbons in a row. Our second one, our 6 carbons are that way. Our third one, our longest chain would start up top here and go this way. The longest chain is going to give us the name of the parent. This has 6 carbons, 1, 2, 3, 4, 5, 6, so it's a hexane, isn't it? 1, 2, 3, 4, 5, 6, this is a hexane with a methyl group. And this is 1, 2, 3, 4, 5, 6, 7, so it's a heptane with a methyl group and an ethyl group. All right, we need to be able to tell where these groups are attached, don't we? For that, we need to number our chain. We're going to number it so that we get a number sequence. And if we have competing number sequences, we want to go for the lowest number at the first point of difference. So we can number it from either end, but we want to go for the lowest number at the first point of difference. If it's a tie, you're going to look at the different parent chains, and we're going to pick the chain that has the greatest number of substituents. So let's look at this guy. What's our parent chain here? Our longest continuous chain. Looks to me like we could do that. 1, 2, 3, 4, 5, 6, 7, right? We could also do that. 1, 2, 3, 4, 5, 6, 7. All right, numbering. We want to number this guy so that we get our lowest number sequence. These, I hope you've noticed, are identical, aren't they? Well, let's go ahead and look at this. Well, compare these two. Well, let's see, wait, back up. These two are identical compounds. We have a methyl group here in our second carbon, 3-carbon chain in our 1, 2, 3, 4th carbon. Those two are identical. There's another way we could do this, and that's this way. 1, 2, 3, 4, 5, 6, 7, with this as a substituent. All right, so which of these are we going to choose as our parent? Remember, we want the greatest number of substituents. So we're going to choose this as our parent, not this guy. This has 2 branches. This only has 1. If we had started numbering here, our first substituent would be at carbon 1, 2, 3, 4. If we start numbering here, as I've shown, our first substituent is at carbon 2. So that wins. All right, finally, well, I guess we didn't name it. Let's go ahead and just finish this and then we'll name some. Look at this guy. First of all, pick out your longest continuous chain. One, two, three, four, five, six, seven, 8. 1, 2, 3, 4, 5, 6, 7, 8. We have two possibilities, don't we? We want the one with the greatest number of substituents then. If we did this one, we would have 1, 2 substituents. If we do this one, we will have the greatest number of substituents. So let's let this be our parent. 8 carbons, it's an octane, isn't it? We have methyl groups here. I let this be carbon 1. So our first substituent here is going to be in carbon 2. We have 2 of them, right? We also, these are methyl groups. We also have a methyl group out here in carbon 6. If we have more than one substituent, we're going to use multipliers, di, tri, tetra, to show where they are. Again, if we have more than one different type of substituents, we're going to arrange these in the name alphabetically. Alphabetically, not by number. All right, so the information we have to relay here about this molecule. First of all, it's an octane, isn't it? We have methyl groups in carbon 2, 2, and 6. We show this as 2, 6 dash trimethyl. And here at carbon 4, we have a 1, 2, 3. I guess, yeah, that's a propyl side chain at carbon number 4. So this is what we're dealing with for our structure. Are we happy with that? Now let's take and write a name. What you have to do at first, list the substituents. Then you put the parent. This is all one word, no spaces, only commas and dashes. We don't alphabetize based on multiplier. So this is methyl. M comes before P, so trimethyl will come first. After trimethyl, we need to say we have a 4-propyl, and then we need to say our parent is an octane. The name would look like this. 2,2,6 trimethyl, 4-propyl, and our parent here is octane. All one word, separated by dashes or by commas. 2,2,6 trimethyl, dash, 4-propyl, no break here, no dash, octane. Now, why do organic chemists worry so much about nomenclature? Not because we enjoy it either, but as we've seen, organic compounds can get very, very complicated, can't they? And it's very important that we be able to describe to each other exactly which compound we're dealing with. So nomenclature really is important. If we had started numbering here, if we made that number 1, our first methyl group here would be in carbon 3, and then 7,7. Propyl group would be in carbon 5. When we talk about number sequence, this sequence is 2,2,6,4. This would be 3775. 2 is smaller than 3, first point of difference. That's why this is correct and this one is not. All right, let's go to the last section here. What if we have a side chain that is branched also? Look at this guy. What's our longest continuous chain? It's 10 carbons. We're going to let this be carbon 1, so our first methyl group here is in 2. Another methyl group here in 3. And then we have this thing hanging out there. When you have a thing hanging out there, the proper way to indicate that is by giving it its own numbering system. By definition, carbon 1 is going to be the point of attachment. So this is carbon 1, carbon 2, and carbon 3. So, on our decane, we have a 3-carbon unit, that's a propane, propyl. And on carbon 2 of our propyl, we have another methyl group. We would refer to this as a 2-methyl propyl. Put the whole thing in parentheses to indicate it's a side chain, and we have to say it's attached at carbon 6. At carbons 2 and 3, we have methyl groups, so that's a 2,3-dimethyl. At carbon 6, we have a methyl propyl group. The full name, 2,3-dimethyl. Then at carbon 6, we have a 2-methyl propyl, and our parent is a decane. Now, just to make this all very confusing, you can also name this by the fact that our side chain has 1, 2, 3, 4 carbons. That's a butyl of some sort, right? It's not an N-butyl. It would be referred to as an isobutyl. Now this nomenclature drives me nuts. The only one that we'll ever use, I promise you, is isopropyl. 1, 2 carbon, parent chain, methyl group. This is called a methyl-ethyl side chain. It's also the isopropyl group. That's very common usage. Everybody will call it isopropyl. That's fine. Or you can name it the other way too. Yep, isopropyl alcohol. Have an OH right here. That's isopropyl alcohol. Isobutyl, the group we just saw. Secondary butyl. This is called tert-butyl. We'll use this a little, where we have the 2-carbon parent and 2 methyls. It's a 1,1-dimethyl ethyl or tert-butyl. This gets very confusing for beginners. I would minimize that on exams and stuff like that, not to just make you crazy. Let's go ahead and look at this. There are 2 ways we could name this. Again, 2,3-dimethyl, 6,2-methyl propyl decane, or we could simply say we have a 6-isobutyl, 2,2-dimethyl decane. Both of these are acceptable. This one makes me crazy. Any questions?
Didn't you say that they are named alphabetically?
Yes, we will arrange them alphabetically. Remember, the di doesn't count, so we're looking at methyl in front of methyl propyl.
Also the iso will count the
Iso
also.
in front of methyl.
Oh,
So for the ISO, you do use the I.
All right, use the iso.
okay,
right.
we don't count the di and try.
Yeah.
Okay.
It's not a di, it's an iso. All right, one last thing here. If we have a halogen attached to it, that's very simple. We just call this chloro, bromo, iodo, or fluoro, and treat it like it's just any old substituent. So here we have an 8-carbon parent. We have methyl groups in carbon 2. We have a propyl group in carbon 4. And up here at carbon 6, we have a chlorine. Go ahead and write a name. Alphabetically, chloro is going to come before methyl, which comes before propyl. We have to say it's an octane, so that's at the end. So I would say 6-chloro dash 2,2-dimethyl dash 4-propyl octane. 6-chloro 2,2-dimethyl 4-propyl octane. Now, how in the world do you ever get good at doing this? Well, you practice lots of problems. Name these guys. First one we look at it and say, oh my goodness, it's a Newman projection, isn't it? I've got to untangle this. Simplest way, I think, is to take the Newman and write it back as a sawhorse. Okay, remember in a sawhorse, we're just going to take our front carbon, move it over a little bit, and it would look something like this. Now it becomes very, very easy. Once again, this is our front carbon, and this is our back carbon. Now you find your main chain. Looks to me like 1, 2, 3, 4, 5. And we have a methyl group here in the middle. There's our chain. We can number from either end. I'll just start here because I can. 1, 2, 3 methyl, and 1, 2, 3, 4, 5, 3 methyl pentane. The next one, find your parent chain. Find carbon number 1. Put in your substituents. I could have chosen any of these methyl groups for my parent chain, but I just did that one because I want to. We want to start numbering at this end, so our first substituent is that carbon number 2. We have a 1, 2, 3, 4 carbon parent. It's a butane with methyl groups and carbon 2. Any questions? Yeah.
Will you ever give this to us backwards? Like you'll give us the name and we have to draw the solvers?
Oh, absolutely. In just a moment. Hang on. Absolutely. What if I took and I changed our methyl group here into a chloromethyl group? Huh? So instead of this, I put a chlorine here, and let's just put one here too. Go ahead and name this guy. Now we need to come up with a different parent, don't we? Because we want the most substituents. So we're going to want like this to be our parent. This way we have chlorine as a substituent, another chlorine, and two methyl groups as substituents. Where is carbon number 1? Well, it's going to be here, so we have a 1-chloro, right? That'll be our lowest number. We still have 1, 2, 3, 4 carbons, so it's a butane. We have a chlorine in carbon 1 and carbon 3. And we have 2 methyl groups in carbon 2. This would be 1,3-dichloro, 2,2-dimethyl butane. Yeah.
Let's say if you didn't have the chlorine on the third carbon,
Uh-huh.
would you still put the 1, or can you just
Yep.
have this one?
Yeah, it would be a 1-chloro. If we didn't have this one, it would be a 1-chloro, 2,2-dimethyl.
Is that chloro or is that monochloro?
Nope, just chloro. All right. We will do a lot more nomenclature at the end of class with the sheet that I give you for practice. But let's just return to the concept of conformational isomers again. And let's look at it from a slightly more sophisticated stance. Remember we said we have free rotation around our sigma bonds. Therefore, we can have rapidly interconverting isomers. These are conformational isomers. And because they interconvert so rapidly, we just regard it as the same compound. The truth is, however, that some conformational isomers are preferred energetically. That is, they are lower energy than others are. So in the mix that you get, you will have a slightly higher population of the lowest energy conformer. Let's just start off with something very simple, with ethane. Let's draw ethane in 2 conformations. I will call this one eclipsed and this one staggered. In eclipsed, I have this arranged so that the hydrogens here are both sticking straight up. It would be equivalent to this as it goes around. In an eclipse, all of these actually are lined up. Over here in the staggered, we have hydrogen down, hydrogen up. If you think about it, this hydrogen is in between these two. Now, in this movie, as it rotates, take a look as this hydrogen gets up, so it's eclipsing this other one. It gets pretty close, doesn't it? Now, when we do a space-filling model, this is approximately 90% of the electron cloud for that particular atom. So actually, as these things get really close here, they do interact with each other. And that makes the eclipsed less favorable than the staggered. We can actually plot out an energy for this as this thing rotates. As we go from eclipsed to staggered, this is about 12 kilojoules per mole difference in energy. Our prediction, therefore, would be that at equilibrium, because it's all equilibrium, we would have a slightly higher population of eclipsed than we would staggered. This is referred to as steric hindrance. Steric refers to size, and hindrance just means they're in each other's way. In organic chemistry, side chains are going to be big. Steric effects are going to be important. And this is just an example. Now, here it's not quite as clear as it would be in a butane. Here's a butane is kind of in a sawhorse configuration. One methyl group is pointing up, one methyl group is pointing down. So this is a staggered conformation, isn't it? If I convert this into a Newman, sort of, it would look like this. Let's go back. Here's the front carbon, here's our back. Front carbon, back carbon. And we can see our two methyl groups are on opposite sides of our molecule. Right? Okay, what I want to do is rotate around this single bond so I bring our methyl groups into different conformations. This is the movie for it. In this guy, you'll note that when we hit the eclipse up here, so the two methyl groups are both pointing up, you see how they overlap each other badly. That's going to be lots and lots of steric hindrance. Let's go through the full family. This is the staggered that we started with. Now I'm going to rotate around this bond 60 degrees. So I've taken my methyl group here, moved it from here down to here. Everything here is eclipsed now, isn't it? Our two methyl groups aren't, but all these hydrogens are now eclipsing each other. That's bad. Another 60 degrees. We're down here now. We're not eclipsed anymore, but our methyl groups are getting closer together. Another 60 degrees. We're down here, fully eclipsed everywhere. This is really unhappy. And then we rotate. This is the same as this one. And then finally back to where we started. Let's go ahead and look at the real energetics of these. Here's our little movie again. We're going to start off with these things staggered. This is also referred to as anti. They're on opposite sides. They're anti to each other. Our first rotation brought us up here to this. We will call this one an eclipsed gauche. It is higher energy because it's eclipsed. Our next one, we're down to a full gauche where we don't have eclipsing anymore. That is more stable, but less stable than the anti. Another rotation, we're up here to eclipsed gauche again, although this is fully eclipsed, isn't it? Down here to gauche. Here's our eclipsed gauche, same as this one, and then finally back down to the anti. The energy levels here are much more significant. We're talking 16 to 19 kilojoules per mole as a barrier for this rotation. The point here is to do two things. First of all, this is a more sophisticated look at conformational isomers. Again, we can make the prediction that in a simple butane, we would have more of the anti at equilibrium than we would eclipse or the eclipse gauche. It's all in equilibrium, they're all the same molecule, but we have more of these guys too, at equilibrium than we do the eclipse. The other point of this is to introduce the concept of steric hindrance. When we do cycloalkanes in the next chapter, we'll see that interactions such as this really can be destructive as far as determining the conformation of a particular compound. Any question? All right, let's go ahead and go back to our nomenclature. And let's do this backwards. Take these names and give me structures. What you want to start off with is your parent. It's a decane. So you want to zigzag with 10 carbons. In carbon number 6, we're going to have a 2-carbon side chain. That's an ethyl group. In carbon number 4, we're going to have an isopropyl group. Remember, isopropyl is a 1-methyl ethyl. So it's a 2-carbon branch with a methyl group in carbon 1 of the branch. This would be an acceptable structure. There's our parent chain. This is carbon number 1. In carbon number 2, 3, 4, 5, 6, we have an ethyl group. In carbon number 2, 3, 4, we have our isopropyl or methyl ethyl side chain. Now again, you could have drawn this absolutely straight. You could have tied it in a knot. Any conformation works as long as you have a 10-carbon parent and your appropriate side chains. 2-fluoro, 3-methylpentane. Start off with a 5-carbon chain. Choose one end, make it number 1. Carbon 2, we're going to put a fluorine. Carbon 3, we're going to put a methyl group. Here's our compound. There's our parent. Carbon 1 here, 2-fluoro, 3-methyl. Our next one's a heptane. You want 7 carbons in a row. Define one as carbon number 1. We'll deal with this in a second. We're going to put chlorines in carbons 3 and 5. Now, what in the world is this? It's a dibromo ethyl. So that means we have a side chain with 2 carbons on it. It's in position 4. Now you look at your side chain. Remember, is defined as being attached through carbon 1. So on our second carbon, we're going to have 2 bromines. 7 carbon parent. Carbons 3 and 5, we put chlorines. Carbon 4, we're going to have a 2 carbon side chain. On the second carbon of this side chain, we will have 2 bromines. Our parent looks like this. I'd let this be carbon 1. So carbon 3 and 5, I have chlorines. Carbon 4, I have a 2 carbon side chain. 1, 2. On the second carbon of my side chain, I have 2 bromines. Any questions? Start off with the parent, 7 carbons. Define the carbon number 1. We have 2 chlorines at 3 and 5. We have a 2 carbon side chain, that's an ethyl group, 1, 2. And the second carbon of this, we have 2 bromines. All right, simple problem here. Draw me 1,2-dichloroethane in the anti and the gauche conformation. Now you could use a Newman, you could use sawhorse, you could just draw lines. Newman's is a little more sophisticated. In the anti, we're going to have our Newman. Our chlorines are going to be opposite each other, aren't they? Now, if we rotate this 60 degrees, we would get eclipsed gauche, wouldn't we? We don't want that. So to get our other gauche, we have to rotate it 60 and then 120. So the gauche would look like this. I guess I rotated that carbon up. The same thing. All right, which of these would be the most stable? Methyl groups are big, chlorines bigger. We take and we try to eclipse 2 chlorines, it would be very unhappy. This is what the molecule looks like in the anti-configuration. See how big our chlorines are. If we stuck the chlorine up top here, it would be all over each other's face. And finally, let's do one very simple problem here. Here's a ball and stick. Go ahead and just name this compound based on the ball and stick model. You got to be able to convert from one to the other. It's all the same. You just find the longest chain, define carbon number 1, so we get our lowest sequence, and then look at your side chains. Our longest chain here is going to be 1, 2, 3, 4 carbons, I believe. And we have methyl groups in carbon 2 and 3. Now, isn't that simple? All right, we are going to take about a 10-minute break. You can waste it any way you want, or you can sit and start working on very, very simple nomenclature, isn't it? We look at our first compound here, we have 1, 2, 3, 4, 5, 6, 7, 8 carbons in our chain. So it's going to be an octane, right? We need to decide which end of the chain we're going to make carbon 1. If we start down here, our first substituent would be in carbon 3. Therefore, this is carbon 1, gives us our lowest number sequence. We need to say that in carbon number 3 we have a methyl group. In carbon number 5 we have a 3-carbon side chain, that's a propyl group. 3-methyl, 6-propyl, octane.
Oh, question.
Question?
Yeah. Why is the 6? The 6?
1, 2, 3, 4, oops, 5. Sorry. Change that to a 5. You see, I do this on purpose every now and then just to make sure people are paying attention, that's all. That's all.
Okay.
All right, our next one. We have 1, 2, 3, 4, 5, 6, 7, so it's a heptane, right? Now, we're going to number 1 at one end of the chain or the other. If we started here, our first substituent would be at 3. If we started here, our first substituent would be at 3, 3. 2 3s. 2 3s are better than 1. Therefore, this is carbon number 1. We're looking at 3, 3, 5. If we started here, it would be a 3, 5, 5. 3, 3, 5 is better at the first point of difference. So we have 3 methyl groups. It's going to be a trimethyl. We need to say 3, 5, 5 trimethyl heptane. Our next one here, 1, 2, 3, 4 carbon, it's a butane. We want to let this guy be carbon number 1. We're going to have a 2,2 dimethyl, and it's a butane. Any questions? We have a 3-carbon parent, don't we? Either one, anyone, could be carbon number 1. And we simply have 2,2 dimethyl. Our next one, our longest chain is going to be 1, 2, 3, 4, 5. So it's a pentane, right? We have 2 ethyl groups here. and they're attached on the middle carbon. So it doesn't matter which end we make carbon 1. And we're going to have a 3,3 diethyl pentane. Our next one, we also have a pentane, don't we? And we have a methyl and an ethyl attached to our middle carbon, so it doesn't matter which one we make number 1. We're going to arrange our two substituents alphabetically. Ethyl comes first, then methyl. They're both at carbon number 3. 3-ethyl, 3-methyl pentane. This guy up here, we have 1, 2, 3, 4, 5, 6, 7, 8 carbons. So it's an octane. Have a whole bunch of methyl groups on it. We're going to let this guy be carbon number 1. So our first substituent here would be carbon 2. Now we just have to count our methyls. We have 1, 2, 3, 4, 5 methyls. That's going to be a pentamethyl. And we need to say where they are. They're carbons 2, 3, 4, 5, and 6. 2, 3, 4, 5, 6, pentamethyl octane. Makes you feel good if you get it right, doesn't it? Okay. Great reward in organic chemistry. Our parent here is a butane. We have 4 carbons. Going to let one end of this be carbon number 1. Then we're going to put methyl groups in carbons 2, 2, and 3. So you draw your butane, find carbon 1, and stick in 3 methyl groups. Here is our butane, right? We've defined carbon number 1. In carbons 2, 2, and 3, we have methyl groups.
So if we always say where all the, say, methyl groups are, say there's 5 of them like that, why do we still have to say penta? Isn't that kind of redundant?
Well, no, what was here?
Oh, well,
No, that's right, so you need the number sequence.
well if
If
I'm
we had
saying,
moved one of the methyls to here, it would be 2, 3, 4, 5, 7.
Yeah, no, I mean like 2, 3, 4, 5, 6. Why is it not just methyl octane? Why are we saying penta still? If we can just count 2 through 6.
I don't know, the rule is you have to put in multipliers, okay?
Right?
Don't argue with the IUPAC. International Union of Pure and Applied Chemistry
I'm
makes
just
the
curious.
rules.
Someone spent a lot of years.
We just follow the rules.
I'm
Here
just
we have a
curious 'cause
hexane.
I thought there might be a reason for it. Okay.
Hexanes, 6 carbons. It'll let one end be carbon 1. We have an ethyl group in carbon 3. And we have 2 methyls in carbon 2. Ethyl group in carbon 3, 2 methyls in carbon 2. Here we have an octane, zigzag with 8 carbons. Let one end be carbon number 1. we are going to have 6 methyl groups now. At carbons 2, 3, 4, 5, 6, and 7. So it looks like that. Any questions? Let's go to the resonance one. Should be able to draw resonance structures just as quickly as you can draw the structure. All we're going to do is take an electron pair and move it up here so we neutralize the carbocation. When we do that, it's going to generate another carbocation. We would show this way. Move the electrons up to here. We took them away from this guy, so it is now positive. Our next resonance form, we can take these other pair of electrons here, move them in to neutralize the carbocation, and that's going to leave this guy electron deficient. And that would be our third carbocation. Our prediction here would be that in this carbocation, we would have positive character up here, here, and here.
Dr. Young?
Yeah.
Why is the double bond moving counterclockwise?
Oh, doesn't matter.
Oh, it's either way, okay.
It's all entirely arbitrary. All right, let's do another one here. Another carbocation. We're going to do the same thing. Move electron pair in to neutralize it. And that's going to leave this carbon here electron deficient. If we do this again, we wind up with this carbocation. Again, our prediction would be that in this molecule, we would have positive character at carbons 1, 3, and 6. Our next one is a great friend. It's called the benzyl carbocation. When you have an arene, so a benzene ring, we'll call this, with a carbon attached to it like this, that's referred to as a benzyl group. Benzene, benzyl. Benzyl carbocation is relatively stable. Draw resonance structures to explain why it is so nice and stable. Step 1, we want to take electrons from the ring, move it out to neutralize this. We've now placed our positive charge in the ring. Step 2, we can move this electron pair up to neutralize it, putting our positive charge here. Step 3, we can move this electron pair up, putting the positive charge here. And then, of course, we could move the electron pairs from our CH2 back in to regenerate the one we started. The more you spread out the positive charge, the more stable it is. Here we have put the positive charge on 4 different carbons. Any questions? Let's do a similar one now. We're going to do a cyclopentadienyl anion. Carbocations and carbanions are not very stable, but as far as anions go, this is a fairly stable carbanion. The exercise, we're going to take the electron pair from the negative carbon, and we're going to move it into the ring. When we do that, if we put it here, that would put too many bonds on this carbon, so we have to move this electron pair out. And we'll localize it on this carbon. And we would show this way. Move it in and move it out. We're going to do the same thing again. We're going to move these in. Put too many bonds here, so we have to move this out, localize it on this carbon. Now, because this is a 5-membered ring, if we do the operation again, moving it in, we're going to localize it out to this carbon. And finally, one more time, move it in, move it out. And if you're keeping score, we have now placed the negative charge on each of the ring carbons. They each have a minus 1/5 charge. Again, we have spread out the negative charge. That makes it stable. We'll see later on that this is what's referred to as an aromatic compound because we have 6 electrons that we can move around by resonance this way. This is what it actually looks like. Here's our electron cloud in the middle, and you see we have uniformly placed the negative charge on all carbons equally. Finally, this is an oxocarbonium ion, carbocation adjacent to an oxygen. Remember that oxygen has 2 unshared pairs of electrons. Therefore, we can move one of these electron pairs in to neutralize the positive carbon. That's going to put 3 bonds on our oxygen. Remember, oxygen with 3 bonds has a positive charge. Think H3O. This is the other resonance form for the oxocarbonium ion. When I was a postdoc many, many years ago, I did a paper on oxocarbonium ions. We actually devised a method to measure the lifetime of these guys in solution, in water. It's about 10 to the minus 9th seconds. All right. Let's move to our next one. A little more nomenclature. And a fuzzy compound. These are kind of fuzzy because these are out of the database that's on Blackboard. So I put them in Blackboard and then I copied them out. Probably shouldn't have done that. But, so these are examples of the quiz that you're going to take on Blackboard. There'll be compounds like this. Step 1, you look at it and you find your longest chain. This is a chlorine here, so we have 1, 2, 3, 4, 5, 6, 7, 8. It's an octane. I'm going to let this be carbon 1. That'll make our chlorine carbon 2. So we have a 2-chloro, and then up here, let's see, this is carbon 1, 2, 3, 4, 5, have a 5-methyl. 2-chloro, 5-methyl octane. Our next one here is one of these Newman projections, but we can deal with that. Our front carbon here, we have a methyl group, so that's 1, 2. Our back carbon is carbon 3, 4, 5 as our longest chain. I'm going to let this be carbon 1. We have carbon 1, 2, 3. On carbon 3, we have this CH2Cl. We're going to call this a chloromethyl side chain. Now, we don't need it to call it a 1-chloromethyl because methyl group only has 1 carbon, doesn't it? So, don't need the 1, but this is a chloromethyl side chain. 3, chloromethyl pentane. If we let this guy be carbon 1, we would have 1, 2, 3, 4 as our parent. 5 is better. And finally here we have a chloromethyl group here, a CH2Cl, and we have another chlorine dangling off here. Obviously we're going to have 1, 2, 3, 4 as our parent. We're going to let this be carbon 1. I think. There it is. Now it's carbon 1. We're going to have a 1, 2, 3, 1, 3 dichloro. In carbon 2 here, we're going to have 2 methyl groups. So it's a 2,2 dimethyl. Just put all your pieces together. 1, 3 dichloro, 2,2 dimethyl, and our parent is butane. Yeah.
Can you break down the Newman into isomers for me?
Well, I can't without doing it on the board. We'll do that after class.
Right.
Okay? All right. Here we have 1, 2, 3 carbon for our parent. Right? we're going to have a bromine and a methyl group on carbon 2. Our parent is going to be a propane, so we write that. On carbon 2, we have a bromine, so that's a 2-bromo, 2-methyl propane. Our longest chain here, 1, 2, 3, 4, 5, 6 carbons. We have a 2-carbon side chain and we have a chlorine. We're going to let this end be carbon 1, so we get a 1-chloro in our name. In carbon number 3, we have a 2-carbon side chain, that's an ethyl group, so 1-chloro, 2-ethyl, hexane. Our next longest chain here is going to be 1, 2, 3, 4, 5, 6, 7. So it's a heptane, isn't it? Write heptane down. We have a bromine attached out here at our first carbon. This would be our second carbon if we started numbering there, so we'll let this be carbon 1. Now we have 2 ethyl groups. They're in carbons 2, 3, and 4. And we have a chlorine down here in carbon 1, 2, 3, 4, 5, 6. Our chlorine is carbon 6, bromine is carbon 1. So we're going to do a 1-bromo, 6-chloro, 3,4 diethyl heptane. Please put a dye in here. I'm sorry, I left that out.
I forget too.
Isn't it supposed to be 3, 4?
Right, 3,4 diethyl.
I have a question.
Okay,
The brom is a carbon 1.
right,
Oh, okay.
because that gives us our lowest number sequence. If we started numbering here, our first number would be 2. On an exam, you will have nomenclature, going both ways. Now, these are probably comparable to what you will see on your first hour exam. Two more here. Pretend this is an exam question. Our longest chain, going to be 1, 2, 3, 4, 5, 6, 7, 8, 9 carbons. It's a nonane. Probably want to start numbering down here, so we have a 2-methyl group. We're going to have a methyl group in carbon 2. We have an ethyl out here in carbon 2, 3, 4, 5, 6. And a bromine also in carbon 6. We're going to arrange these alphabetically. So it's going to be a 6-bromo, 6-ethyl, 2-methyl, okay, this is not the correct name at all. This is for the other compound that was here that didn't show up. Okay, so once again, let's just ignore this word there. That's the wrong name. We have 1, 2, 3, 4, 5, 6, 7, 8, 9. It's a nonane. That's carbon 1, 6 bromo, 6 ethyl, 2 methyl, nonane. Lastly, you look at this and say, oh my gosh, what is this? It's a square tacked on the end, isn't it? Well, we're going to do cycle of alkanes in the next chapter, and we're going to refer to this as a cyclobutyl group. 4 carbons, it's a butyl. Cyclo, they're in a ring. So we're going to deal with this just as a substituent. Okay? That means that our parent is going to be 1, 2, 3, 4, 5. Attached to carbon 1, we have a cyclobutyl group. Attached to carbon 2, 3, 4, we have a methyl. So I hope this is the right name. We'll see. 1 cyclobutyl, 4 methyl pentane.
For the cyclos, do you include the C before anything?
Yeah, you do the cyclo. Just like iso. All right. Refreshingly easy. Quickly look at these and just give me functional groups, main functional groups, not the carbon chains, for each of these compounds. Our first compound is a carbon-carbon triple bond. What is that called?
Okay.
That's an alkyne. It also has a nitrogen attached. That's an amine. Our next compound, we have a little three-membered ring here. Not going to worry about what that is. Cyclopropane, actually. But we have a CH2OH here. That's an alcohol, right? And we have a COOH. Remember, the CO is a carbonyl. We write it out this way, COOH, that's fine. This is a carboxylic acid. For our next one, we have a 6-membered ring here with 3 double bonds. Remember, we will learn that that is benzene, but the functional group that represents is an arene, A-R-E-N-E. We also have an oxygen here attached to 2 carbons. That's an ether. In this next guy, we have a carbonyl, and we have a nitrogen on one side. Remember, that's the backbone of proteins. That's called the amide functional group. We also have a sulfur that's attached to 2 carbons. Remember, if that was an oxygen, it would be an ether. If it's a sulfur, we call it a sulfide.
What's the difference between amine and amide?
Carbonyl. Our next guy, This is the other way to write a carboxylic acid. Remember, we abbreviated it as COOH. Here we actually show the carbonyl OH group makes it a carboxylic acid. And finally, here we have a carbonyl with an O something attached. This is a methyl group, can be any carbon thingy at all. This is a derivative of a carboxylic acid. It's a carboxylate ester.
Why isn't it just called an ester?
You could call it an ester, yeah. There are different, as you get more into organic chemistry, there are different types of esters. So carboxylate ester requires that the carbonyl be there. All right, this is fun. Draw the structure of an aldehyde that is C3H6O. Aldehyde is a carbonyl, and attached to one side is a hydrogen. So the way to do this problem is we know this is the end of our chain, right? All we need to do is come up with 2 more carbons, 5 more hydrogens. Gee, C2H5, that sounds like an ethyl group, doesn't it? And finally, we want 2 ketones that are C4H6O. Remember, a ketone is a carbonyl with a carbon on both sides. Let's start off with a carbonyl. Now I just put a methyl group hanging out there, just because I could. Now we are missing, so this is 1, 2 carbons, we're missing 2 carbons. We've used up 3 of our hydrogens, so we have 3 hydrogens left. 2 carbons and 3 hydrogens. How do you do that? Well, we're going to take and extend this out, right? That'll give us 1, 2 carbons. We only have 3 hydrogens, so we need a double bond. All right. Now get the other one. Draw another one. Start off with your carbonyl. Draw 2 lines, because we have carbons on both sides. Once you do that, you only have 1 more carbon to work with. There you go.
Oh, okay.
Called a cyclopropanone. And then finally, isomers. Are they identical, different, or isomeric? Our first compound here, C5H12. This is C1, 2, 3, 4, 5, 6, H14. Those are different chemical compounds. Our next one, we have 1, 2, 3, 4 carbons, a methyl group, and we have 10 hydrogens. This guy, we have 1, 2, 3, 4, 5, 6, 7 carbons, and 14 hydrogens. Once again, they are different chemical compounds. Our next guy, we have a chain of 1, 2, 3, 4, 5, 6 carbons. Here we have a chain of 1, 2, 3, 4, 5, 6 carbons. Have a chlorine on carbon 2, chlorine on carbon 1, 2, 3, on carbon 4, right here. They are both C6H12Cl2. Again, chlorine on carbon 2 and 4, 2 and 4, they are identical.
I have flipped in my head isomer.
Yeah,
Can you show me how you're counting the carbons in not the solvers but the other one?
this one,
Yeah.
carbon 1, carbon 2, 3, 4, 5, 6.
Thank you.
Here we have a chain of 1, 2, 3, 4, 5 carbons. Here we have a chain of 1, 2, 3, 4, 5 carbons. On carbon 1, we have a chlorine. Carbon 1, we have a chlorine. On carbon 2, 3, right here, that's the carbon 2, 3, we have a chlorine and a methyl. Chlorine and a methyl. They are both C6H12Cl2, and they are identical.
Did you say it's like 5 carbons?
Hmm?
5 carbons, right?
Yeah, 1, 2, 3, 4, 5.
So C divided by
6.
where?
5 carbon parent,
Oh.
and then the methyl. Our carbon chain here. Let's let this be carbon 1. I guess we let this be carbon 1, wouldn't we? So carbon 1, 2, 3, 4, 5. Right? And we have a methyl group here in carbon 2, a methoxy in carbon 2. 1, 2, 3, 4, 5. Methyl group in carbon 2, methoxy in carbon 2. I think this is wrong. I think they are identical, not isomers. Please change that. was late at night when I was doing these. Sorry. So let's get that off. And finally, look at these guys. Our carbon chain is 1, 2, 3. Our carbon chain here is 1, 2, 3. We have a chlorine in both. We have the same molecular formula. However, this is a chlorine attached to carbon 1. This is the chlorine attached directly to our triple bond. They have the same formula, same numbers and types of atoms, but they're arranged differently. Constitutional isomers. Our last set here. We have a carbonyl attached to a nitrogen that makes it an amide, right? Our nitrogen has a hydrogen and a methyl. Here we have, after our carbonyl, we have 2 carbon chains. After the carbonyl, we have a 3 carbon chain. Methyl group here dangling down. These two have the same molecular formula, C5H11NO. They are arranged differently. They are constitutional isomers. Here we have a 3 carbon chain attached. Here we have a 2 carbon with a branch. Same formula, different constitution.
So it's 11 carbons, 12, hydrogen.
The nitrogens are the same. They both have a hydrogen and a methyl. And we have a carbonyl, CH2, CH2, CH3. Here we have a carbonyl, CH, CH3 with a methyl side chain. Yeah,
When you write the stick structure, how do you show just the CH, not a CH?
a CH. It would just, well, we would just, you'd drop the line like that. Yeah. Remember, you always assume it has 4 bonds. Yeah.
So if those were identical, then on the software structure, you would need to have methyl groups coming out of the chain.
And our last one here. We have a 6-membered ring, don't we? We have a carbonyl in our ring. So we do. Start at our carbonyl. Carbon 1, carbon 2, we have a methyl group. Carbon 1, carbon 2, we have a methyl group. These two are identical. Six-membered ring, carbonyl, carbon 3 would be a methyl, carbonyl, carbon 3, methyl.